So, good afternoon to all of you.
Good
Can you
afternoon, sir.
see the PDF?
Good
Please reply
afternoon.
if
Good
you can
afternoon,
see.
sir.
Good afternoon, sir.
Thank you. Good afternoon to
Good
all of you.
afternoon, sir.
Good afternoon, sir.
Afternoon.
Good afternoon, sir.
Good afternoon, sir.
So, कोई बचा भी है गुड आफ्टरनून बोलने के लिए?
No, sir.
बोलो तो फिर स्टार्ट करते हैं, कोई बचा है तो. So reply if you can see the PDF, this PDF, updated PDF.
Yes,
Yes,
sir.
sir. Yes,
Okay,
sir.
thank you. So today we'll discuss a new concept known as prime numbers and related concepts. So we'll start with interesting result. I'm talking about proposition 2.1.1. It's not so important. Important is lemma 2.1.2. But before that, we discuss this simple proposition 2.1.1. And we say that suppose we have three integers and one of them is non-zero, say a. So we have three integers a, b, c, where the integer a is non-zero, and see what is condition here. If it's a conditional statement, if a divides b and also a divides c, then we can conclude that in this case a divides product of b and c. This is your result, and proof is not so lengthy, and just proof is a two-line proof. So just I write the proof. Just I'm going to read out the proof of this proposition 2.1.1 and see what is information we have. So this much information, think about, again I'm recalling that the statement in between if and then, this information you have and you can use anywhere inside the proof. And after the term then, this is your concluding remark and you have to reach at this point. So this is two terms. One, we have this information which lie between if and then. So this is if a divides b and a divides c. This information we have and we can use anywhere in between the proof. And you have to conclude what is concluded just after whatever coming after them. That means you have to conclude a divides product b and c. So this information we have. The information is a divides b, where a is non-zero, because by default we have to assume that divisor is always non-zero. That's why a is non-zero. We have a divides b and also a divides c. So by formal definition, you can write b as a, you could think as b as a factor of a. That means b is, can be written as a times some integers r. So I write here b is nothing but a into r, where r is some integers, and also c. This is another information, a divides c. That means c can be written as product of a with some integers I call s. So c can be written as a dot s, where s is some integer. So that's why this is a formal way to writing. If a divides b and a divides c, then b can be written as a times r and c can be written as a times s for some rs which are integers belong to z. Now after that, we consider this product BC, because just we observe that B is nothing but A times R and C is nothing but A times A. So just you consider product of BC. So B dot C is same as, just you replace B by AR term and C by AS. Just I replace and put this one AR AS, and then after that we can manage in this way. So this BC can be written as A times ARS. That means, by what do you mean of that? Means BC has ARS times A. Means BC has a factor as A. BC has a factor A. That means A divides BC. So this is a formal verification of this proposition, and mathematical verification of any statement, mathematical statement, we call the proof. So that is why I tag as a proof. That means A divides BC. So this is an easy proof. It is not difficult. Now, but think, just reverse statement of this one. So if A divides BC, can you say that A divides B and A divides C? If A divides BC, can you conclude that A divides B or A divides C? And see, what I will write after this proof, that converse of this above proposition 2.1.1 is not true in general. Why? Because we have counter example. See, B is integer which divides product 8 and 9. So think about here, A is equal to 12, B is equal to 8, and C is equal to 9. That means A divides B into C. But we cannot conclude that in this case A divides B and A divides C, or A divides C, because see that the 12 divides A into 9, because 8 into 9 is about 72, and 12 also divides 72, but 12 neither divides 8 nor divides 9. So A divides B and A divides C, so we can conclude that A divides product of B and C. But in reverse way, if A divides BC, we cannot conclude that in this case A divides B and A divides C, because we have a counter example, and this is your example, counter example. Now,
Sir, sound not clear.
please. Maybe some network issue, because weather is not so clear today. So in this situation, I cannot help out because weather is not in my control. Now, look at lemma 2.1.2. And this mathematical statement is known as Euclid lemma. Euclid lemma. So this mathematical statement is known as Euclid lemma. And what this lemma say that, suppose we have three integers A, B, C, where A is non-zero by default, because we are going to divide by A. If A divides BC, product BC, and also this another information, GCD of divisor with one part of this product is 1, B, I call B is 1. Then in this case, we conclude that A divides C, another component of the product. So see how this lemma is structured. Suppose we have three integers A, B, C, where A is non-zero, and another information is given that if A divides product of B and C with another condition, which is given that GCD of A and B is 1, that means A and B are relatively prime. In this case, the divisor A divides another component C of the product. So this is the celebrating results of number theory. So proof is also not lengthy and just write the proof here. See what is info. First you note what is your information and what is your conclusion. Means what is given, what you have to conclude. So this information you have. What is information? A divides BC. One information you have. Another information we have, A and B are relatively prime. Relatively prime. So these two information we have in this lemma, and using these two information, we'll conclude that then A divides C. A divides C. This is your concluding remark. So we have to reach at this point anyhow, just using by this two given information, A divides BC and GCD of AB equal to 1. We have two information. Using these two information, you have to conclude that A divides C. So we start the writing looking for the mathematical verification known as a proof. So C, what is information? GCD of AB equal to 1, another is A divides BC. Now I use one information first, GCD of AB equal to 1. So since, that's why I write, since GCD of AB equal to 1, then we know that GCD can be written as linear combination of A and B. Here GCD is nothing but 1, so 1 can be written as ax plus by for some integers xy. Okay, then always remember what is your goal, and in that direction you have to move. Then what I write here, then I consider the term C, and C can be written as, because C is an integer, C can be written as C times 1, and in place of 1, because 1 is, it can be written as x plus by, so in place of 1 you can write x plus by, just replace 1 by x plus by. So I got this sentence, and then just remove the bracket, then we can write acx plus bcy. Now this is a given information, A divides BC. This is given information, A divides BC, and another information we have, A divides AC, because you can easily see that A divides AC, because AC has one factor A. AC has one factor A, and this information already given. What is given information? A divides BC. So A divides AC, then A also divides AC times X, and A divides BC, then A also divides BC times Y. So A divides sum of these two ones. That's why I write A divides ACX plus BCY. Then A divides ACX plus BCY. Hello, sorry for disturbance. So we are here. See, again I'm recalling the proof because GCD of AB equal to 1, so 1 can be written as linear combination of A and B. That's why I write A1 is equal to X plus BY for some integers XY. Then we consider the term C, and C can be written as C times 1. In place of 1, because 1 is same as X plus BY, just replace 1 by X plus BY. Then we got this term. Now, this information we already have that A divides BC. This given, and we know that A divides AC because AC has one factor A, and that's why A divides this combination AC times X plus BC times Y, and that means A divides ACX plus BCY, and ACX plus BCY is nothing but just we have observed that C same as ACX plus BCY. That's why A divides C. So that is your goal in this lemma. With these two information, A divides BC with GCD of AB equal to 1, then we just reach that A divides C in this case. This is clear lemma. If anyone have doubts, you can ask. Okay, thank you then. Now, just I recalling the term prime number. I believe that all of you know this about this term. So a prime number, also known as a prime, is any positive integer greater than 1 which has only two divisors, 1 and itself. So prime number are also known as a prime. These are the positive integer greater than 1, means 1 cannot be, by the formal definition we cannot treat 1 as a prime because by default definition that any positive integer greater than 1 we call a prime number if its divisor is, positive divisors are only 1 and itself, and any integer greater than 1 which are not prime we call a composite number. This is all about prime number and composite number. Like if you ask that what is the example for prime number, so you can see 2 is a prime number. What is the reason behind? Because divisor, positive divisor of integer 2 is 1 and 2 only. You think about 3, if you claim that 3 is a prime number, that means you can look for the positive divisor of 3 and you can see that 1 and 3 itself are only positive divisor of 3 and so on. Then just I list few prime numbers, first prime numbers like 2, 3, 5, 7, 11, 13, 17, 19. So 1, the integer 1 is neither prime number or nor a composite number by formal definition of these two terms, prime numbers and composite numbers. Now come to this mathematical statement. I quote as a theorem 2.2.5, and this mathematical statement say that suppose we have two integers a and b and we have a prime, suppose p is a prime, such that this prime p divides product of a and b. In this case we conclude that p divides a or p divides b, means at least one of the factor is divided by the prime p, at least one. So see what is information we have in this mathematical statement, that p is a prime number This is the first information we have. Another information we have, P divides this product AB. Using these two informations, we'll conclude that P either divide A or P divides B. So this is your goal. We have to reach at this goal using these two given information. Just note down your informations. Your information is that P is a prime number and also P divides the product of A and B. And just also note down your goal. You have to reach at this goal. So suppose P divides A, so we don't have to write anything. If anyhow we get that P divides A, then we don't have to, because we are looking for either at least one of must be divided. Either P divides A or P divides B. If P divides A, we don't have to move anywhere and your goal is solved. So let us assume that P does not divide A. This is a symbol for does not divide A. And C, P is a prime number, and that means only positive divisors of P is only 1 and P. That means GCD of PA is equal to 1. Because P is a prime number, so we cannot get any factor except 1 and P does not divide A by assumption. That means GCD of P is equal to 1. And see, this is the next information we have, that P divides AB. Then we obtain P divides B because GCD of P is equal to 1. So use Euclid algorithm lemma, just we have discussed Euclid lemma. Euclid say that any number A divides BC and GCD of AB equal to 1, that then A must divide C. That's why here GCD of P equal to 1 and P divides product AB. That's why just by using Euclid lemma, we can conclude that P divides B. So at least one of them is divided by P if P is a prime number and P divides product of AB. If P divides A, we are done. If P does not divide A, we just conclude that in this case P divides B. So this is the interesting observation about prime number P. If P divides product, then P divides at least one factor of the product. And you can generalize this statement 2.2.5 for any two product of any two integers, more than two integers. So just I write this proof. If anyone is interested about this proof, you can read out the proof. Just I write as this statement as a corollary 2.2.6. So just I reading out the only statement. Suppose we have n integers and we have a prime P which divides this product a1 a2n, then P must divide at least one factor I call ak in between a1 to n. And also write, I have written the formal proof of this one. You can read out, and if you, and then also correlate 2.6, this is based on this one. It's not so interesting. Now this is the lengthy statement. The proof is so lengthy, so just you concentrate on the statement of this mathematical statement. I quote as a theorem 2.2.8, and this statement says that any positive integer greater than 1 can be expressed as a product type prime numbers. So by using this proposition 2.2.a, we can think a prime numbers as a building block of positive integers, because any positive integer can be written as any positive integer greater than 1. Any positive integer greater than 1 can be written as the product of prime numbers. So prime numbers that we can think as a bricks of the positive integers, because if you suppose that we have number 15, the 15 can be written as 3 into 5. 3 into 5, 3 is prime number, 5 is prime number. So 50 can be written as 50 can be think as a product of primes. So that means any integers like 100 we have. So 100, can you write 100 as a product of primes? Anyone? Please reply if you have the answer.
Two square into five. Sorry.
2 square into 5 square. Yes, good. So see that in 100 we'll get 2 times 2 and 2 times 5. So that means you think prime numbers as a brisk जिससे प्राइम इंटीजर्स बनता है just by using the multiplication operation. So that's why prime number is so important. Suppose you want to know about integers, we just know the all the prime numbers, it is enough, because any positive integer greater than 1 can be written as the product of prime numbers. And then I something. Now come to the another concept, and this known as Fermat's theorem. Fermat's theorem. This theorem, just I'm giving the statement. I started the writing the proof, but that could not complete. In next lecture, I will just write and show the proof, complete proof. Yeah, even if you want to read this proof today only, you can look the Barton book, David M. Barton. We have discussed about this proof on in next previous lecture. So see the statement of this Fermat's theorem. This is a very interesting result in number theory. And you can think of this theorem as a lever saving device in certain calculation in number theory. So what is meaning of this result? Suppose we have a prime number p, and also we have an integer I call a, such that p does not divide the integer a. See, three information we have in this Fermat's theorem. We have three information. We have prime number p I call, we have another integer I call a, and another third information is that third and important information is that p does not divide a. Then using these three
सर स्क्रीन नहीं
information,
दिख रहा है.
सर क्लोज हो गया स्क्रीन से.
sorry. Please reply if this screen is now visible to you. Anyone?
Yes, sir. Yes, sir.
Sir.
Thank you. So I'm talking about Fermat's theorem, and this theorem you can think of as a lever saving device. Just using this one, you will get you can reduce your calculation part in the number computation. So what is meaning of this theorem? So in this theorem we have three information. We have prime number p. We have a prime number, I call the prime number as a p. We have an integer, I call that integer a. And the third and most important information is that p does not divide that integer a. Using these three information, we conclude that with this information, a is congruent, A power P minus 1 is congruent to 1 modulo P. That means P divides A power P minus 1
सर
minus 1.
स्क्रीन शेयर फिर से क्लोज हो गया
Sir,
सर.
again screen vanish.
Okay, 1 minute, please. Wait. Maybe some network issue. And I think now it's okay.
Yes, sir.
Okay.
Yes, sir.
So with these three information, we conclude that A power P minus 1 is congruent to 1 modulo P. That means P divides A power P minus 1 minus 1. That is meaning of this symbol. If you say A is congruent to B modulo N, that means N divides A minus P. So here in place of A we have A power P minus 1. In place of B we have the 1. So with this information, that means what is the meaning of this line statement? P divides A power P minus 1 minus 1. So this is your Fermat's theorem. This theorem is also known as Fermat-Little theorem. Why Fermat-Little theorem? Because this theorem is given by these two person, Fermat, this is one mathematician, and another mathematician Little. That's why this theorem is also known as Fermat-Little theorem. So please, when you write this, sorry, again, I think the screen is lost. Some issues. So when you write Fermat-Little, both F in capital, L is capital, because both are mathematicians, both are person. So this theorem is also known as Fermat-Little theorem. So in this theorem, we have three information. We have prime number P, we have an integer A, and we third and most important information we have P does not divide A. Using these three information, we conclude that A power P minus 1 is congruent to 1 modulo P. That means P divides A power P minus 1 minus 1. That means another way you can think at, if you divide A power P minus 1 by P, then you will get the remainder 1. Then you will get the remainder 1. In another way you can think, if you divide A power P minus 1, P is an integer, A is also integer, P is prime, A is integer, and when you divide the number, that maybe number is big, A power P minus 1 by P, then you will get the remainder 1. So I started the but could not complete the proof. In next lecture we will discuss proof of this theorem also. So based on this theorem, why this theorem is important, we will see the based on this theorem we have some question. Suppose that you want to look for the remainder when this big quantity 5 or 38 is divided by 11. Suppose we have a big quantity 5 or 38 and someone asks to you that find the remainder if this quantity 5 or 38 is divided by 11. So see, we have already discussed about how to find the remainder, but using this Fermat's law we can reduce your calculation. Why? I'm going to show that. See, here your divisor is prime, 11. So just you take P as 11 and A is equal to 5. Then you use your Fermat's theorem. Fermat's theorem in this case say that A power P minus 1, in this case A is equal to 5, P equal to 11, A power 10, P minus 1 is nothing but P is 11, so P minus 1 only means 10. So 5 power 10 is congruent to 1 modulo 11. So using the Fermat's theorem, we'll get the 5 power 10 is congruent to 1 modulo 11. Now, So by just using Fermat's theorem, you got this. What is when you divide 5 or 10, this big quantity is not square, not cube, not power 4. This is a big quantity. 5 or 10 is a big quantity. You can write in simple way, see that how many term is coming in 5 or 10. So this Fermat's theorem just allow us to write in this way, just by using any computation. And if you just do some calculation, you can see that this statement is true. When 5 or 10, I think it's a big quantity, very big quantity, 5 or 10. And when this number is divided by 11, we'll get the remainder 1. That is meaning of that. That means 11 divides 5 or 10 minus 1. Now, this information we have, and obviously this Fermat's theorem reduce our computation, because just we reach to this point 5 or 10 is congruent to 1 modulo 11, but we have to reach till 5 or 38. Our goal is to reach to 5 or 38. When this quantity is divided by 11, what will be the remainder?
वॉइस क्लियर नहीं आ रही है सर.
Maybe network issue, my friend, and I can understand your situation, but system is not my control. Try to understand my situation. Our university is closed and we are forced to teach online. Now see, just by using Fermat's theorem, we got till this computation that when you divide 5 or 10 by 11, we get the remainder 1. But this is not your ultimate goal. Our ultimate goal to find remainder when 5 or 38 is divided by 11. What we do here, then we write 38 just by using use the division algorithm between 38 and 10. That's why I write 38 can be written as, by using division algorithm, 38 can be written as 10 times 3 plus 8. And C, then 5 or 38, we simplify, then 5 or 38 can be look like this one. Now see that just we have seen that 5 or 10 is congruent to 1 modulo 11. Then using basic property of congruence, we can see that 5 or 10 power 3 is also congruent to 1 modulo 11. So this line. And we simply observe that 5 square is congruent to 3 modulo 11. Then 5 square, just to do make power of 4 both sides by using elementary properties of congruence, we'll get 5 square power 4 is congruent to 3 power 4 modulo 11. Then you can write here in this way 5 power 38, because this quantity is congruent to this quantity is congruent to 1 modulo 11, and this quantity is congruent to 3 modulo 11, That's why instead of 5 power 10 is power 3, you just write 3 1, and instead of this one 3 power 4 11. And this is just to do that one. 3 power 4, 3 power 4 is nothing but, anyone reply? 3 power 4
81.
is nothing but
81.
81. So 81 modulo 11 is same, 81 is same as 4 modulo 11, because 81 minus 4 is congruent to modulo 11. If you divide 81 minus 4 by 11, you get the remainder 0. So 81 modulo 11 is same as 4 modulo 11. That's why I write here 5 power 38 is congruent to 4 modulo 11. That means if you divide 5 power 38 by 11, we'll get the remainder 4. So process lengthy, but see, using Fermat's law, we reduce our computation. Just we reach to this point 5 or 10. Then we have to look for the remaining part. So we do some calculation here, and we got the remainder 4 when 5 or 38 is divided by 11. Come to the next question. I'm talking about problem 3.1.2, and this is also a big number, big data. And this question say that find the remainder when 50 power 250 is divided by 83. That means compute this term 5 power 50 power 250 modulo 83. That means what is the remainder when 50 power 250 is divided by 83? This is the short way to write the term remainder using your Fermat's theorem. So here I also did some computation, and you can easily see that Fermat's theorem reduce your computation to some extent, not completely, to some extent. So see the solution. First you point out that the number 83 is a prime number. 83 is a prime number. So then you can use and you choose A is equal to 50, A is equal to 50, and P is equal to 83. Then using the Fermat's theorem, we'll get this term. Fermat's theorem says that A power P minus 1 is congruent to 1 modulo P. Here P is equal to 83, A is equal to 50. Then we get the A power P minus 1 means 50 power 82 is congruent to 1 modulo 83. So see, we got this term. That means if you divide 50 power 82 minus 1 by 83, we'll get the remainder 0. Yeah, we see that when you divide 50 power 82 by 83, we'll get the remainder 1. So till this extent, we simplify our computation. So remaining part we have to look for. Then till reach we got the 50 power 82. We have information that when we divide by 83, we'll get the remainder 1. Now what we did after that, we used the division algorithm between 250 and 82. Then 250 can be written as 82 times 3 plus 4. Then just start, because our ultimate goal to find the remainder when this term 50 power 250 is divided by 83. So 50 power 250 can be written in this one, because 250 can be written 82 times 3 plus 4, sorry. Then we just write in this way. And this one, the simple computation. I believe that all of you agree on this one. Then 50 power 82 is congruent to 1 modulo 83 by using the Fermat's theorem. So just write 1 power 3 into 50 power 4 modulo 83. and 50 power 4 is nothing but this quantity, big quantity. Because now we don't have any method to simplify, so just to do simply division by 83 of this quantity. So you can see that because this quantity is lesser than 50 power 250, so now you can easily divide this number by 83, you get the remainder 17. So that means when 50 power 250 is divided by 83, we will get the remainder 17. And based on today's discussion, we have listed some question for you. Please try to find the remainder when 200, 2 power 1000 is divided by 13. Please try to compute the remainder when 2 power 1000 is divided by the number 13. I should mention here that 13 is a prime number. Please try to find the solution, that means remainder, and post your solution on the common WhatsApp group. I believe that some of you are interested in the number 3 concept, and I hope many of you will try to solve this question. Not all, I also believe not all will try, but some of you will definitely try. 3. Can you post your solution on common WhatsApp group? Please. So that everyone can see your solution.
Sir, answer is 7.
See, we cannot guess. Please send your solution on the common WhatsApp group, please. Your solution can be wrong, can be right, doesn't matter. For anyone, not only for me, anyone. And don't worry about your solution. Can be wrong, can be right. Whatever writing, post your on the common WhatsApp group so that I can also cross check, and many of you also can see your solution and comment on that. Your solution may be wrong, may be right, doesn't matter. You should not worry about correctness of your solution. If you're trying, please post your solution on common WhatsApp group. So borrow 83, 4, good. 2, 4. So what is your answer? Anyone?
3,
What is the correct answer?
3.
3, sir. 3.
Yes, not 8. I don't think 8. How you get 8? Just by looking the Anil Gupta post, I am seeing that answer could be 3, not 8. Because see that by using a Formet's theorem, we reach to that point 2 power 12 is congruent to 1 modulo 13. And then what he did, just divide 1000 by 12. Then the quotient is 83, I think, and the remainder is 4. So finally you have to look for the 2 power 4. And 2 power 4 is nothing but 16, I think. And 16 is congruent to 3 modulo 30.
3 mod-
No, 4 modulo 30. 4 modulo 30. Something wrong? 16 is congruent to 3 modulo 13. So that means your answer is 3. I am reading out the solution of the Anil Gupta, whatever he post, and I think the answer is correct.
Yes.
If you anyone a doubt, you can comment on this one. If any of you have some doubts on this question, this answer, you can comment. Then I received the Abhishek and Abhishek. What Abhishek got? 3. Yes, Abhishek, your answer is also 3. Good, thank you. Then Puneet got 3. Good, thank you, Puneet. Then Artika, 1 minute, Artika. So you got the same, yes, 3. Your answer is also correct. Yes, same procedure. Good, thank you, Ankita. And then yes. So many of Solni, I received Solni, Sujoy, hard have a solution. Sujoy 3. Good, thank you. Sujoy, your answer is correct. Thank you. Then Solni,
Sir.
just I'm reading out the solution. How you found this one? 2 on this one, A4, A9, A6. Good, thank you, Solni. Your answer is correct. So finally, we got 5 to 6 solution from your side, and all the solution is correct. Now try to solve the second question. That means find out remainder when this big quantity 6 power 2000 is divided by 11. Procedure is same. Please, if you know the solution, please post on your common WhatsApp group. Whoever solve this question, please post your solution, so that I can also cross check your solution, as well as your friend also cross check your solution. And don't worry about the correctness of the solution. Maybe right, maybe wrong. So just received solution from one Thakur. Who is Thakur? Maybe Soli Thakur. Who is Thakur जी? ये ठाकुर है कौन? ये रोल नंबर किसका ना, ये मोबाइल नंबर किसका? 80 यूपी बिहार के ही होंगे ठाकुर जी. कौन है ये? इन लोगों की आदत है नाम बदलने का, ठाकुर, सम्राट, इसे नाम रखने का. कौन है ये? ठाकुर रखने थोड़ी अब सोले के वो बन जाओगे बसंती वाले. मैंने कहा पिछले लेक्चर में कहा था अब नाम चेंज करके आओ. कल से ऐसे मैं नाम देखूंगा पहले ब्लॉक करूंगा इस ग्रुप में. whoever. ठाकुर है कौन? मोबाइल नंबर 8726578280. कौन है ये? इनको भी ब्लॉक कर रहे हैं. सुदर्शन हो क्या? सुदर्शन
सर नाम ही उसका ठाकुर है.
ठाकुर ही नाम है?
सर सुजय कुमार ठाकुर.
नहीं, सुजय कुमार ठाकुर तो नहीं है. इस लड़के का रोल नंबर में ऐसे ठाकुर गौरव सिंह है क्या नाम?
हेलो सर.
अटेंडेंस में ठाकुर गौरव सिंह नाम है।
हेलो सर।
हाँ यस प्लीज।
सर मैंने डाला था मेरा नाम करेक्शन में, मेरा नाम उसमें गलत डल गया था।
क्या लिखा है आपका नाम?
मेरा नाम सर पूरा गौरव ठाकुर सिंह है, उसमें गौरव सिंह सिर्फ दिया गया है, इसलिए मैंने करेक्शन में बोला था।
इसमें क्या नाम लिखे हो आप?
वही सर, उसमें मेरा पहले इस व्हाट्सएप में है ठाकुर गौरव सिंह, लेकिन मेरा नाम गौरव ठाकुर सिंह है।
इसमें तो ठाकुर गौरव सिंह लिख रहे हो।
यस सर।
जो करेक्ट नाम है उस पे आओ दोस्त। कि घुमा के परमुटेशन कॉम्बिनेशन क्यों कर रहे हो? इतना परमुटेशन कॉम्बिनेशन क्यों नाम के सब कर रहे हो? कल से सिंह भी पहले खींच ले आओगे, बीच में अच्छा लग रहा है तो। ये परमुटेशन कॉम्बिनेशन आपके घर तक सही है। जो आपका अटेंडेंस शीट में नाम है उसी नाम से आपको आना है। आप एप्लीकेशन दीजिए, नाम वेरीफाई हो जाए तो फिर नाम चेंज करिएगा। ये परमुटेशन कॉम्बिनेशन मुझे अच्छा नहीं लगता है। इस नाम से मैं उसी नाम से जानना चाहता हूं जिस नाम से आप यहाँ पे इनरोल हुए हो। गजब गजब लगता है। एक हमारे दोस्त है, बता रहा हूं, उनका नाम वीरेंद्र सिंह है और वो अपने नाम को घुमा फिरा कर रखे हैं बागी बलिया वीरेंद्र सिंह राजपूताना। और परमुटेशन कॉम्बिनेशन जब नाम होता है वो चेंज करते हैं, परमुटेशन कॉम्बिनेशन काफी करते हैं। उनको नाम में क्या परमुटेशन कॉम्बिनेशन करने से मिलता है आई डोंट नो। ऐसे ही भाई साहब ये बैठे हैं, कनेक्शन दिया गौरव ठाकुर सिंह तो घुमा को ठाकुर को बीच के इधर खींच के लाए हैं। अगले क्लास से किसी का भी नाम उल्टे सीधे नहीं आने चाहिए, मैं तो पहले ब्लॉक करने वाला हूं। आपके नाम से आगे पीछे का मुझे इंटरेस्ट नहीं है, क्योंकि मुझे काफी दिक्कत होता है। मैं अटेंडेंस अपने पास रखता हूँ और देखता हूँ कुछ दूसरे नाम से कोई जुड़ गया है। So now try to see that our time is over now, and we have listed these 4 questions one by one. Please try to solve all of these 4 questions, and if I get some time I will include more and more questions based on the Fermat's theorem, and we'll discuss in the next lecture. Okay, till that, thank you, thanks to all of you. And one thing also, if you write the solution, maybe right, maybe wrong, doesn't matter, but post your solution only on the common WhatsApp group so that I can read the solution, and also as well as your friend also see that solution. Okay then, thank you, thanks to all of you.
Thank you, sir.
Thank you, sir.
Thank you, sir.